Okay, now in this problem, we're going to be analyzing a couple of reactions and determining whether this reaction is product favor or reactant favor for both of for both reactions. Okay, so let's see what happens here. We have acetamide and reacting with sodium ethoxide. So let's do this now. And to give, this is ethyl acetate, and this is sodium amide. Let me write it down. Sodium amide, which will be plus, negative here, and this is ethyl acetate. And here I have acetamide. And this is sodium ethoxide. So, and what this reaction is about, we're doing an acyl substitution. We're going to have the nucleophilic attacking here. So, to determine where the equilibrium is going, let's analyze what species are more reactive, or we can also say less reactive, so more stable. So, when we have our scale of reactivity, we'll learn that amides are the least reactive of all. And the reason for that is that even though we have an atom that is connected to this carbon that is more electronegative than carbon, yes, it's true, but we do have resonance effect, even though the inductive effect points at making the carbon more electrophilic. Turns out, let me highlight that again, that we have important resonance effects here. And you can do this structure. And in this resonance structure, you can see that here, the carbon is not as electrophilic. So now, that decreases the electrophilicity of that carbon, making this less reactive. Plus a bad leaving group, the amide anide. So, the least reactive of the series. The ethyl acetate is a little, the esters are a bit more reactive. So, least reactive of the series, so the most stable. Where is the equilibrium going? Towards the more stable species. So, amides essentially are more stable than esters because they're being less reactive. So now, this equilibrium is going to be shifted over here. So, it's not favoring product, it's favoring the reactant side. Also, we can see here in terms of the other molecules that we're forming. Here's sodium amide in the alkoxide. Here, when you have sodium amide, this is the conjugate base of ammonium. So amide anion. Here, pKa is 38. And here, sodium acetate is a conjugate base. Ethoxide is the conjugate base of ethanol. Here, the pKa is 16. So, stronger acid, weaker base. And this is much a stronger base. So, here is the weaker. So, when we analyze acid-base reaction, the equilibrium always is shifted to the weaker acid, so a weaker base. Here we have weaker base, stronger base, and this is more stable than that, so the equilibrium is pointing to that side, so it's reactant favored. All right, let's analyze the other reaction. That's a little bit more difficult because here you have oxygen attached to the carbonyl. Here again, same thing. So in reactivity wise, the esters is likely more reactive than the carboxylic acid. But let's look now. The stability is telling me that kind of maybe equilibrium, so I have all the species there. So now let's analyze the acids here. Here, that's an alcohol. So the pKa of alcohols in general are around 16, except for terbutanol, that is 18 due to steric considerations and solvation. But nonetheless, this is around that. But what is the pKa of water? Well, this is 15.7, which is about the same. So structure-wise, same electrophilicity here. The nature of the living group here, OH is bad living group, but it's also OR is a bad living group. So slightly better, but again, the equilibrium maybe is slightly favoring the, not either side. It could be favoring that way, but in reality, this is about the same. So I'll say that's a true equilibrium and that we will have OR for the species.